thing, but we're excited to have Matt here to talk to us. But I'm gonna turn it over to Sarah for introductions, and then we'll get going.
I'm very happy to introduce Matt Lodge, who is a fourth-year PhD student from the University of Bristol, where he works with Hannah Wigford and Zoe Langford. Never say her last name out. And Matt works on all things cloud scattering, which is what he's going to tell us about today.
Yeah, hi guys, thank you very much for the invite. So we're getting to the stage now where we can start looking at these planets and working out things like maybe whether there's liquid water on the surface, and as well as the distance that the planet is from the star. It also matters how well it's retaining that sunlight if we want to answer that question. So it doesn't just depend on how far it is away, it really depends on how well it's holding onto that radiation through greenhouse gases or how much it's reflecting through clouds. So what's happening in the atmosphere is really important. And that's basically what most of my research is focused on. And so we start in the atmosphere of these planets with what we know from Earth's atmosphere already. And this is science that we've done for a long time. But we know that the particles that we have in our atmosphere can have a dramatic effect on the temperature of the Earth. And there are lots of different sources of particles that can exist in our atmosphere. Some of them from things like wildfires, there's fossil fuels, volcanoes, and all these things contribute to the energy balance of our planet by either reflecting or absorbing light that exists high up. And so the solid and the liquid matter in the air can absorb or reflect light, and that changes the balance of energy that we receive from the sun. So from all the radiation that comes in, on average, roughly 24% is reflected by the clouds, and then a further 23% is absorbed by the atmosphere. And that's before it even hits the surface. So if we want to try and figure out what's happening at the surface, that's why it's so important to consider what's happening in the atmosphere. Zooming in on that, you can often see the effects. So the whole east coast of the States last year was kind of covered in this opaque orange haze from the wildfires in Canada. And so we can visually see this strikingly through smogs and hazes on Earth. But there are other more measurable metrics that we can use as well to see how these affect us. So after Mount Pinatubo's eruption in 1991, there was a huge increase in sulfates, and that cooled the entire Earth's temperature on average by 0.5 degrees, which is pretty substantial. And as a result, the next 2 years afterwards were the coolest years from the past 35 years. So we can see the effects that these particles are having. On other bodies, extending this further to the solar system and beyond, we know that on Titan there's thick hydrocarbon layers of cloud and haze that dominate the upper atmosphere. So it's kind of like that last photo on steroids, and we get this kind of beautiful orange glow as a result. And we expect most detected exoplanets to also contain significant amounts of aerosols in atmospheres. We know that these particles exist on every major body in the solar system, and we're expecting them to exist in places beyond that as well. For example, using JWST, we can actually measure spectroscopically which chemicals, which minerals the clouds are made of. And then from that, we can basically form models to try and work out what shape, what size they are, and how much light they absorb. So there's just one example taken here, which the TSD Dreams team found some silicate clouds. And I'll show you the spectra of that later and talk a little bit more about it. So zooming into the atmosphere of all these places, how do we actually model it? Once we actually figure out which substance it is, what do we do to generate a model of this atmosphere? Well, most optical models so far assume that all particles are spherical as a first approximation, for two reasons. First of all, it's quick, and secondly, it's simple, but it's not necessarily correct. And this is basically where I started my PhD, this idea that actually, well, if we're making this assumption, how different could reality be from what the models are suggesting if we assume that all the particles are spherical? And so we can take particles on Earth. This is some TEM images of aerosol solids that we found on our planet. And you can see that it's often not the case. These particles are definitely not spherical. They look a little bit more like bunches of grapes. And if you model individual particles more accurately, they can actually be a lot more absorptive, up to 1,000 times more absorptive than their spherical counterparts. And that's exactly the same material, exactly the same minerals, but just literally unwrapping them from a sphere into this fractal shape. And you can show that they're much more absorptive, but actually putting that into models is unfeasible because it involves loads and loads more calculations. And so we wanted to basically say, well, is there a better way to do this? Is there a fast way to get accurate calculations for these particles? And then we can see how that's going to affect our assumptions of what's in the atmosphere of these planets. So which optical properties do these models actually need? Well, effectively, the light that comes in can either be scattered or absorbed by the object. And so there are three kind of key parameters that you look at. So you take the cross-section of the area of light from an incoming parallel beam that's been absorbed, add it to the amount of light that's been scattered, and then totally, if you add those two together, that's called the extinction cross-section. And even this is really interesting. This is kind of the bit that kind of got me gripped on the topic to start with. But you'd think from incoming beam of parallel light that the biggest amount of area you could ever remove, your total extinction cross-section, would just be equal to the cross-sectional area.
That's screen it. I'll come back and see
At the back.
It's online, it's not good.
Oh, cool.
Yeah.
So I'll just say that again. So you think from an incoming beam of parallel light, the biggest amount of area you could ever remove would just be your geometric cross-sectional area of your sphere. But that doesn't happen. So in real life, especially when your wavelength is near your particle size, waves don't behave like you'd expect them to geometrically. They have interference and diffraction, and you can actually end up having an extinction cross-section, which is way, way, way bigger than your actual particle. And we've seen up to 30 times larger than the particle size, just because waves interact really weirdly with shapes, right? And that's just for spheres. So it's already non-intuitive for the spherical case. So calculating this for a bunch of grapes actually becomes like a really, really difficult mathematical problem. But there's a few different ways we could do it. And the first paper I did with Hannah, we basically compared three different theories. So one of them is me theory, and that's a super fast theory. It's basically the spherical assumption. And the way that it works is it's literally an analytical solution for how Maxwell's equations are going to interact with something that's a spherical body. And so because there's lots of symmetry in that, you can actually do the maths for it. It's complex, it's pretty gnarly, but the end result is quite elegant, very beautiful. And as a result, it's a good one to use as a first approximation. There's very few free parameters. You just check in the wavelength, the particle size, the material type, and you'll get a cross-section out of that. But as I said, one of the problems is it's too simple. And sometimes it underestimates absorption by a factor of 1,000. So although it's quick and simple, it's not necessarily the best one to use.
Yeah, if it's gonna keep doing that, why don't you skip having the Zoom over there? Why don't you put your slides?
Yeah, shall I skip screens?
That's too. Sorry about that.
That's all right, no problem. Okay, bear with 1 sec.
Is it literally just the screen?
I think it's just a
We're
little
gonna
bit.
do that.
We told Michelle.
I'll tell them
Yeah.
after this, yeah.
I think we had it there in our meeting too, last.
Sorry.
That's okay, no problem at all.
And then, sorry, on Zoom, I think it's still grabbing.
Oh, yeah, the wrong screen. But they're now looking at themselves.
So, yeah.
Yeah, it's not.
Beautiful, perfect. All right, thanks, man.
No problem. So the second theory that we looked at is called modified mean field theory. So this is a little bit more complicated than me, and as a result, it's more accurate. So you don't get these huge offsets of factors of 1,000. And it's pretty fast because it's an approximate theory. There's only a few simple parameters that we have to put into this one, but it does have some restrictions. So all monomers have to be the same size of material, and actually, in the long wavelengths, it doesn't necessarily always give you the right answer there as well. So we also wanted to benchmark it against something that was a more rigorous theory. And the one that we chose is called the discrete dipole approximation. So it's a bit of a misnomer. Basically, the way that you use this theory is you break it up into as many dipoles as you possibly can. So you take your realistic shape, break it into little cubes. And in theory, it would actually be exact if you can have infinite dipoles. Although it's called an approximation, the only reason it's an approximation is because you can't have infinite dipoles. It just depends computationally what you can handle effectively. But this uses the exact shape, the exact composition. You can have different polarization states of light, angles of light coming in. And so it's really, really comprehensive as a rigorous benchmark theory. But especially when we started, it was thought to require a really, really big number of dipoles. And that makes it much, much, much slower than the other two. And I'll show you exactly how much slower in a second. But those are the three theories that we compared. And we then went about getting some actual realistic particle shapes. So to begin with, very kindly, Kuji Adachi, Pete Busek, and Serena Chung provided us with some real actual particles that they captured by flying a plane above Mexico City with a filter on the bottom, and then took the particulates that they found. This is basically just soot particles from like car exhausts, effectively. They get lofted up into the atmosphere. And they put these through a TEM from lots of different angles, so you can get different slices and then actually reconstruct the exact shape of the particles. And despite the best efforts of the team, These are still a little bit blocky towards the end, so you can see that they're kind of made of Minecraft, these particles. So maybe they weren't the most realistic shapes. And so the first thing I did as part of my PhD here was make some codes to increase the resolution of the particles to try and smooth the edges and make them a bit more realistic.
A question about scale.
Oh, sure.
Those, were they, are those similarly sized, like to scale?
Yeah, good question. So the scale is kind of like microns size, and
Okay.
there's actually a big range that can happen between them. So you can actually have particles that are down to like 0.01 microns, and then they go up to like 10, depending on the material type. So they can really range as well as shape in the actual total mass as well.
Okay, cool. Yeah, I wanted to know if those particular particles were approximately the same size as each other.
Good question.
Because they are shaped so differently and.
Yeah. That's a really good question. So I'd imagine what's more likely is that the monomers are the same size. So the individual spheres that make these up are probably more likely to be the same size, if anything. So this one would be much longer as a scale.
Okay.
Just because the way that these form, providing they form in the same conditions, that the monomers are like kind of what form to start with, and then they stick together and kind of coalesce into an aggregate. And so if you end up with different shapes, because you might have the second stage where they stick together being under different pressures and temperatures, different conditions. But the initial monomers growth, that depends on like the initial temperature where it formed, which is probably going to be the car engine or something like that, like the immediate cool downs at least. So I'd imagine that'd be the case, but actually it's not necessarily always true. Question. So smoothing these. So this is just a small chunk of middle one, and you can see on the right, we made this algorithm called Spherify that kind of rounds the edges and basically just doubles the resolution in each of the X, Y, Z dimensions. So each of these 1 dipoles becomes 8, and then you can kind of take one or add one to make the edge a little bit more smooth. And it also decreases resolution. So we call the backwards squarify. And you might be thinking, why do we do that? Well, it's computation time. By increasing the resolution, we now have a much more realistic shape, but we've times the amount of time to actually calculate any optical properties by a factor of 10. So you can also do the inverse and get a much faster calculation. And we're basically, the point of this first paper was how far can we push this in terms of decreasing the resolution so that we still get an accurate result, but we can save ourselves lots of time computationally. And that was basically the purpose of the first paper. And I wanted to go into a little bit more detail about why it's taking so much longer. Like, it's easy to imagine, you've got more dipoles, but specifically, like, you can explain why it is it actually takes a lot longer. So if we just take a system of 3 really simple dipoles, the way the DDA actually works is light will basically hit one, and then you look at the phase difference by the time it scatters to hit all the other ones. And then that's a pairwise calculation that you have to do for each of these dipoles. So you're solving how light is going to interact, how this electromagnetic field is going to interact as a kind of pairwise phase calculation for all these dipoles. So you end up with solving a big system of linear equations for 3n times your number of dipoles. So this is the kind of the math that we've got. So some key variables. So m is the refractive index. That's the chemical, the material that you're putting into your model. X, Y, Z are your dipole positions, and you also have the angular wave number. So that depends on the wavelength of light. And basically, these diagonal terms, you have these kind of 3 by 3 tensors, and the zeros just happen because of a little delta function here. The alpha term depends on refractive index. And then if you look at what else we've got in this term, so we've got refractive index again, dipole size, the B1, B2, B3 are just coefficients. So again, m is just refractive index, k is the wave number. And so all these terms are depending on are things that you could set up for your scattering problem. You know what material is, so you know what their refractive index is, and you got your shape, so you know your dipole width. So you have all that information as you start your scattering problem. The other terms in this big matrix on the left, so these are given by, again, the wavelength of light that you're using. R is the distance between these dipoles as a hypotenuse, and then you got the X, Y, Z positions. So again, this is basically just depending on the wavelength of light and the positions. So the actual the spacing of these dipoles geometrically. So again, we have everything on the left, and then the stuff on the right, this is all to do with the electric field of light. So looking at this one, we've got the wavelength of light, again, the dipole spacing, we've got 2 spherical polar angles, which are going to be the direction that you fire your incoming beam of light. And then finally, you got the polarization state of the light. So whether it's Y polarized or X polarized. So the reason for showing you all this is to say, right, we have everything on the left. We know for a particular shape of particle, a particular effective index, a particular wavelength, we have all the stuff on the left. We have all the stuff on the right. And so we need to calculate this stuff in the middle. And so what it becomes is just a big inverse matrix problem. And whilst you can invert a 3x3 matrix equation like this by hand, 4x4 becomes very tricky. This is only for a 3 dipole system, and we've already got 9x9, which you can solve on a computer. Take a very long time by hand. Recently, I had to do a 4 million dipole shape, so 12 million by 12 million array of linear equations that you have to solve. And so this is why it becomes computationally intractable to do anything with large numbers of dipoles. It's interesting, the way that you solve it is numerically. So rather than actually solving this analytically and getting the exact values, you effectively take a guess at all of these using something called the biconjugate gradient method. And you then multiply your matrix out. So you take the top one, multiply by P1, add a 0, multiply by P1y, and then see how well it approximates the term on the right. And then there's some clever maths you can use to get a next best guess. Typically takes about 200 iterations of guesses at these values before you get to within 0.1% of the right answers for all of them. And once you have these values, it's really easy. You basically add them all up, times by a number, and that gives you a cross section. But the bit that's hard is basically finding these numbers, just because the matrices are so big when you have big numbers of dipoles. So just kind of highlights the rationale and the motivation for wanting to decrease the number of dipoles as much as possible.
And is this supercomputer computations or is this laptop computations?
Yeah, it depends on what you're doing. So in a minute, I'll show you how low we can push it. And with the low ones, you can do it on a laptop. With the 12 million ones, absolutely, we have to use the high-powered computers in Bristol. Just as a little aside, I wanted to represent, because it's 12 million by 12 million sounds like a big number, but I just kind of wanted to represent exactly what that is, because big numbers sometimes get lost. So if you went out on the floor and then drew out the mathematics for one particle on the ground at the same font size that it is on the TV at the moment, this is the area of land that it would take up.
Oh my gosh.
So they're big matrices. And after the first time I did that calculation, I hugged my computer and apologized. I'm going surfing, I'm going to bed. You do the maths, I'll come back in a bit. Didn't appreciate it fully. But yeah, so this is what we found out. So we're trying to limit the number of dipoles. So we have all our different models here. This is the original one. This is the increased resolution version. And then we got the decreased resolution version down to the point where kind of beyond this, I think there was one more decreased resolution you could do. It's just like 6 random things. So this was about as far as we could go, where it still roughly looked like the original. And what we're plotting here is how much extinction happened as a function of wavelengths for each of these different shapes. And this is for small particles. And what you can see immediately from that is that there's not a huge amount of difference between all of the models, but especially not between the DDA models. So the colored DDA models, it didn't matter which resolution you used. This one took hours on a computer to do. This one was sub-second, measurable time on a laptop, just super, super, super fast. And there was no need to use high-performance computers. You just basically do it with the easy model. Me theory was a little under-predicting, which is interesting to note as well. That's that kind of realistic case that we're talking about. And this was still quite a spherical particle. When you get the longer, more branchy ones, there's even bigger differences between the me theory for spheres and the realistic ones. But when you use the large particles, unfortunately, that's not true anymore. Our lowest resolution one in cyan is the 90 dipole one, and below a certain cutoff point, it started becoming really, really wrong. And then the next one to drop off was the orange one, the next resolution up was 675. And so what the first paper that we did was basically try to quantify where is that cutoff point. How do you know when the wavelength is going to stop being at a point where you're actually going to get accurate cross sections? And so we managed to summarize this quite concisely in a nice equation. So the low resolution DDA can give you accurate results as long as this condition is met. So as long as you have a refractive index, a particle size, and a wavelength, and then this is a numerical factor, which we found to be 2. And if you compute that for a particular scattering problem, it gives you the minimum number of dipoles you would need to use. And you can basically just use that number. You don't have to go higher than that and waste lots of computation time. So that was a good conclusion to make. But actually, one thing that initially was like a little footnote actually became the next most interesting part of my research for the next year. But this tiny bit on the right, it's hard to see because it's not on a log scale here, but this little difference between mean theory and DDA is actually pretty substantial. You can kind of see that from the axes, even though it's not zoomed in. And so absorption can be underestimated if mu and NMF are used, especially at long wavelengths. And that led to some really, really interesting things. So the three next steps I'm going to talk to you about. One of them is experimental proof. So DDA has been around since the 70s, and people have done experimental proof, but as always, it's always good to have more, especially for the exact context materials and particle shapes that we're interested in for exoplanet atmospheres. So I worked with a team to verify that. I'll then talk about this long wavelength stuff, which is really interesting. And then finally, I'll tell you what we're going to do next, which is kind of what I'm doing here with Sarah this week. So for the experimental proof, we can use this DDA theory for verification of lab-based measurements of what we're particularly interested in for some planets, which is cubic potassium fluoride particles. So these are particles that we're expecting to find in the atmosphere of planets. And we can mimic their formation mechanisms on Earth. So Colin Hamill and Alexandria Johnson at the Purdue Cloud Lab basically produced a size distribution of these perfectly cubic salt particles. So this is the size distribution here. Sorry that the number's a bit small, but you've got a number of particles versus mean radius. So it's dominated by this particular bin. But we have this little cartoon at the bottom. We've got loads of different perfect cube particles, all in different orientations, being basically fed into a chamber in an aerosolized form. So it's like a little mini model cloud for this stuff, basically. And then what they did is they shined a laser into this distribution and then measured the intensity of the light that reflected off it as a function of angle. So 0 degrees straight in a line and 180 degrees straight back on itself as a perfect reflection. And so this is the intensity as a function of angle. And to start with, I guess I'll draw your attention to the lab data. So this is the actual curve they got. And initially they were comparing this to spheres. And the curve is much, much flatter than the spherical model. And the reason for that is because spheres are perfectly symmetrical. You end up with resonances that happen in particular scattering directions, just because of how interference generally behaves. So you end up with particular directions that are favorable for scattering, even when you have a distribution of different size spheres. So this is actually the theory for the whole distribution. So even though they're all different size and particle size, you end up with these preferred scattering directions, and it doesn't happen in the data. So what Colin wanted to do was compare it to a more accurate theory. And of course, DDA is purpose-built for this because you're making things out of cubes, and they're cubes. So basically, we did exactly that and plotted a theoretical DDA distribution. And it had some success. So first of all, the feature around the minima is quite nicely matched. And there are generally less resonance features in there. There's still a few little wiggles, but they're much more comparable to the little wiggles that are in the actual data. And definitely not as pronounced. There's the backscattering slope, which is quite unmatched as well. But what's interesting and what came out of this is that both theoretical curves were more intense. I predicted there'd be a higher intensity of light at these higher angles, the backscattering angles, than the actual lab data. And we think that the reason for that is that this actual process of sweeping through the angles took about half an hour. And whilst that was happening, aerosols were basically constantly coming into the chamber. So we think there was probably just like a higher level of extinction that was just generally happening in the chamber to reduce it. Reduce the intensity beyond what you predict by theory. But yeah, it was interesting. And that paper is coming out hopefully soon. It's just comments have gone back to the reviewer. So yeah, hopefully that'll be out in the public sometime soon. But this next bit is, I guess, my passion project. This is the bit I'm really interested in. This idea of how different the long wavelengths are for particles that are realistically shaped. And so we did a study in the Rayleigh regime, which is where the wavelength of light is really, really big compared to your particles. And in this regime, we've known for a long time, hence it being named after Rayleigh, that kind of gives an idea of the scale of how old this is. Calculating the absorption in spheres becomes really, really simple for this special regime. So this is typically like an undergrad equation. You just basically have the radius of your particle, your wavelength of light, and then the two parts of your refractive index. And if you have that information, you can calculate absorption in this regime specifically. There's no complicated interference happening now or diffraction because your wavelength of light is just so much bigger than the particle. So the interaction becomes hugely simplified. And what's really cool is that you can prove this with me theory as well. Again, all these complicated theories, they converge And, summations get truncated and just become this nice simple equation. And just in case you're not familiar with the refractive indices, so n is the real one, and k is the imaginary part of the refractive index. And this is basically what dominates absorption. So for a particular material at a particular wavelength, you just basically read off from the list from nice people that have actually found them in labs, what these values are. And so what I noticed is that when you look at how different the actual realistic cross sections were compared to mean theory, it was always offset, it was always higher, and it was always offset still as a function of 1 over lambda. And so what it got me thinking was, what if you could put a simple multiplying factor into this equation for simple spheres, and it would make it work perfectly for things that are non-spherical? And so I decided to call this model manta ray. It's modified absorption for non-spherical tiny aggregates in the Rayleigh regime. And to understand how it works, you just need a few simple parameters. So we can parameterize our aerosol shape really simply. The exact shape of the aerosol depends on the chemical composition and the conditions where it forms, like I was talking about earlier. But we can characterize the shape roughly using something called fractal dimension, which just roughly represents how compact they are. So a fractal dimension of 1.2 is quite a long shape, 1.9 is quite fluffy, and 2.7 is quite compact. And in theory, it goes right the way from 1 being a perfect straight line to 3 being perfectly spherical. But typically, these are the kind of shapes that we deal with at the extremes. And so what this means, by defining these shapes, we can basically run simulations with lots of different particle shapes. We can take a range of these and do different particle shapes, different chemical compositions, and calculate what would this modification term need to be to go from the spherical model to the actual value in each of these different cases. And so I took 3 of each of these different fractal dimensions and then basically calculated the modification factor. And it's basically representing how wrong they are compared to the spherical model in each of these cases. And this is the set of results. So the modification factors on our upwards z-axis here. And you can see there's basically 3 different patterns. So first of all, the amount that you need to modify your equation depends on n and also on k. So it depends on both parts of the refractive index, not just one of them. It's also interesting that it's highest for things with really low real values, but very high imaginary values of refractive index. And the third really important trend is that it always seems to be highest for the things the longest. And that should make sense, because as you get closer and closer towards a spherical model, as you compact them further and further, you're making them more spherical. And so the amount you have to modify the spherical equation should be less. And spheres are actually plotted on there for reference. Obviously, you didn't have to modify those at all. But we basically ran a pseudosphere in DDA by basically making a sphere out of dipoles just to check that everything was logically working as it should. And yeah, absolutely, you don't have to modify the spherical ones. But if you're not spherical, you end up having to modify it quite a lot. So what I wanted to do was see if maybe there's a way we could empirically define a plane along these points so that people could predictively work out how much they need to modify this equation by. And so we started by fitting something quite simple to this. So this is just a quadratic, but in 2 dimensions. So you've got an intercept term, you've got an n term, and an n squared term. You've got a k term, a k squared term, and then an n times a k term. So it's literally just a standard quadratic, but with 2 different variables. And if you fit that to the data set, it has some success in places, but it's not fantastic. And it certainly doesn't capture the high end very well in any of these cases. So statistically, fitting that equation to the entire data set gives you a coefficient of determination, an R-squared value of 0.71, which is not fantastic. So if you don't use this often, your values can be between 0 and 1. Anything less than 0.5 means your model sucks. Go home and start again. Yeah, so 0.71 is not fantastic. But what I noticed is that you can actually really improve the fit by bimodally splitting this and creating 2 separate functions for 2 distinct regions. So you basically just from this data set, you just take the data where n is bigger than k. So you just did basically just have a line down the middle diagonally and just take the bit where n is bigger than k. This is what it looks like for our longest shape. And then if we fit the same equation just to that half of data, you get a much nicer fit. And the coefficient of determination in this case is 0.99. So that model's really successfully reproducing where your data points are. And we can do the same for all of the rest of that data set as well. I think the laptop's struggling here, that should be rotating, but hopefully you can see it. But basically, for all these cases, didn't matter which fractal dimension you use, just doing the fit for this half gave you a really nice fit for each of these. And we could do the same for the other region as well. So where n is less than k, we can take all that data and then also put it through there. And similarly, we get a good coefficient of determination. 0.92 is not quite as impressive, but it still fits pretty well. And you can see that visually. And what's really cool about this one on the right is it kind of looks like a manta ray as well. So that was just serendipitous. So actually, I'll just get back 1 second. At this stage, I was thinking, okay, this is cool. Someone might want to make a model of an atmosphere, and they might say our particles are roughly 1.5 shapes. And so what we could do is we could give them the coefficients that we found empirically for our data set, and that would help them predict for any refractive index that's not, in our set of grid. They could predict that for anywhere on the plane. But it still seems like there's a pattern here, and you can see that visually with the colors. It still seems like there might even be some trend in the coefficients, because the blue ones are always on the top and the pink ones are always on the bottom. And so I really wanted to find some sort of underlying physics that was maybe explaining this. And we discovered that there's a predictable trend that actually connects the values of the coefficients to the fractal dimensions of the aggregates for different shape types. So if you plot for each of those different fractal dimensions we had, the 1.2 ones, for example, if you plot where the intercept was on the equation that you found the coefficients for, and then you do exactly the same for all the other fractal dimensions, there's actually a really, really nice trend that links all those together. And you can do that for all the rest of the coefficients as well. So we can take A1, A2, A3, all the way up to A5. And I wasn't expecting this, but there is actually like a really, really nice trend that links how these coefficients change for each of these different shapes type. And what this means is that you can have someone who, again, picks a shape, but it doesn't have to be one of the ones you picked already. It could be 1.87 or something like that. And then basically that would allow them to read off from your trends what the values of the coefficients should be to calculate the modification factor. And then once you've calculated those coefficients and you've calculated chi, you can just plug that into your spherical equation, just multiply the number, and you found absorption without having to do 60 miles of math. So it's a really, really powerful equation. You could do this with a pen and paper. And I feel like the culmination of my scientific career so far has turned into a y equals mx plus c. I really thought it was going to be much more complicated. Write a nice letter to my 13-year-old math teacher. That was really useful. So that's really cool. And so, yeah, this code's called manta ray. And if you are trying to calculate absorption cross sections in the Rayleigh regime for anything that's an aggregate, hopefully this can be useful. So just for completeness, this was the set of coefficients you get from our fits to the n bigger than k data set. You remember we split it into two distributions. You can do the same thing for the other side. And actually, if I switch between them, so that's n bigger than k and less than k, you can see that the spread is quite a lot more in the second one. We said the fits weren't quite as good. They were 0.92 instead of 0.99. So arguably, you could maybe put a quadratic through this or something, but I think realistically you want more data before you make a decision. But basically the standard deviation and the errors are just a little bit larger for those kind of data sets. But actually in reality, we end up with less particles where they have imaginary refractive indices that are bigger than real ones anyway. But for the errors that we're dealing with, typically the average is 20% error. The maximum error at any one point for any of these particles was 60%. And this is compared to being 1,000 times wrong, like 3 orders of magnitude wrong. So 60% error sounds quite high, but in the context, it's pretty good considering how simple it is compared to the big calculations. And then the final thing, which is kind of what I'm doing here, is this is all particles in a box, and the next step is to see, well, okay, well, let's make an atmosphere full of them and see what actually happens. How is this going to change our observables? If we have things that are more absorptive than we thought they were previously, what's that going to impact in terms of the climate models that we're making? And so we're looking at the impact on spectra, and we know that these particles cause significant detectable absorption features in the spectra. This is how we know what they're made of to start with. So here's the TST Dreams paper that found silicates that I was talking about earlier. So there's a lot going on in this plot, but for the best well, first of all, direct your attention to obviously the molecules. It's interesting to see what we're finding in WASP-17b, but also the without cloud model is the yellow one, and you can see that we're not matching the data in black very well. But if you put some silicates in there, some quartz, then we end up with a much better fit to the data we actually get there. So that's the kind of thing that we do to find what the particles are in the first place. And what me and Sarah are doing this week is basically saying, okay, well, this will give us a model of roughly how big the particles are, each of the pressure layers in the atmosphere. how is that going to change if we then put aggregates into this instead? If we have more absorptive particles in place of the spherical ones, how's it going to change our assumptions about the model of the atmosphere? So yeah, Sarah and I are working together this week to try to understand how these atmospheric spectra would change if we model the particles with the much more realistic aggregate shapes. And so, in conclusion, aerosols can exhibit substantial absorption and scattering, and it's really crucial to consider them, at least at all, even just with mean theory, in the analysis of these atmospheres. But the accurate calculations don't have to take a long time. You can either use low-risk DDA or manta ray. We determined to be 10 to the power 13 times faster than DDA. I had to loop it lots on my computer to even get it as a clock record, because it's faster than my processor. And we expect aerosols to be everywhere, and early results show that their particle shapes can significantly impact the spectra. But watch this space for Sarah and I. I'll tell you more about that sometime soon. And yeah, the context for this, we've been applying it to exoplanet atmospheres, but actually, as well as solar system objects, another really good context for this would be protoplanetary disks. We're looking at things that are certainly in the Rayleigh regime at this stage. We've got millimeter wavelengths and really small fluffy particles and aggregates. So that's another kind of area that I'm looking to apply this to the context. And maybe it'll have changes in how we, for example, measure the mass of these protoplanetary disks. So that'd be a good place to look for it too. And that's me. So I'll put a link to the code and the paper if you're interested to read it. Thank you very much. Let me know if there's any questions.
Awesome talk, Matt. So yeah, we have plenty of time for questions. So if anyone online has a question, feel free to raise your hand, or you can post it in chat. And of course, anyone in the room, welcome to raise your hand.
Have you tried this on other bodies in our solar system, like Titan or Mars? We know like they're not spherical on Mars, so it's a big question mark. But
Yeah, absolutely. Yeah, there's Titan somewhere I really want to try, especially.
Yeah.
That would definitely be in the pipeline of things to look at. And they're such good laboratories that are much closer to home than the few pixels that we have access to atmospheres. So yeah, that would be a really good thing to do.
I have a follow-up one to that one. That was my question. So 100 years ago, I was looking at the New Horizon results for Pluto, and the big question with that was the layering structure that we see, and that's kind of not so much about the spectrum of what these particles are doing, more about the physical, their physical drag through the atmosphere as they're settling. Is there any way to sort of couple these observational models with something on the more physical end? So you get both like what the observation is going to be, but also what are its physical properties as it's going through an atmosphere of its particles.
Yeah, do you mean like determine what the physical properties were?
Yeah, well, so like if you have a particle, like you had like those ones that are mostly spherical but not quite spherical, can you is there any work being done where you have that shape, you run it through your pipeline, you get the spectrum or what you're expecting, but then that same shape through a different pipeline to get the actual, settling rates of those particles?
Yeah, so the one that we're doing does include dynamics as well.
Okay.
So
okay.
basically they have two kind of key things in Virgo that would be different. So
Yeah.
one is the optic side of things, but then also they're going to behave differently dynamically. So
Okay.
in each of the pressure layers, what it basically does is it's solves for particle size,
Mhm.
but because these fluffy aggregates behave differently, what we're finding is that they form different size particles to what you'd assume for spherical ones. And
Gotcha.
so the way that it works is you have these different pressure layers that go up through the atmosphere,
Mhm.
and you have some vapor to start with. And let's say you have some like convection or some upwelling that's causing the vapor to rise.
Mhm.
Eventually it goes up through the pressure temperature profile until it cools down,
Right.
and vapor condenses out, and then you basically end up with particles.
Gotcha.
And so regardless of whether you use spheres or fluffy particles, the same amount of vapor is like condensing each of the stages.
Yeah.
But you can end up with different size particles based on the dynamics of what fluffy particles would do versus spherical particles.
Gotcha.
And that's the kind of differences that we're seeing so far. And so we have that coupled with the fact you've got optics that are different as well. And then comparing it to other pipelines, that's just one kind of 1D model we have. There are much more complicated things like GCMs that do full 3D, and there are microphysical models that track the growth. And so we absolutely are, that's the first thing that we're doing, is basically comparing it to one of the collisional growth microphysics models.
Yeah.
That has these particles settling and behaving in different ways and different pressure layers to the atmosphere. And actually we've already found, I think, pretty different results. So you're really interesting to
Yeah.
do a big comparison.
Yeah, I mean, for worlds like Pluto and also Triton, like the atmosphere is so thin that these types of physics are extremely dominant. So I definitely encourage you. There's probably Nobel Prizes out there just waiting for you. You go out there and look for awesome
It's
things.
good to have an early nomination.
Yeah.
Heard of Kazumasa Ono?
Yeah. mhm.
So he has, for
Nice.
Triton specifically, has looked at aggregate particles and his model is microphysical one, so.
Interesting. Okay.
Yeah, so Karma is the one, is that one of these microphysical models?
Mhm.
Yeah. Because they're pairing that with ExoCam and other GCMs with that to try.
Yeah, absolutely. Yeah, and so ours is a simpler version, and so that's what we're really interested to basically compare them. We want to see how well.
Awesome.
Oh,
I didn't know. I didn't see what that was.
We want to see how well the Virgo performs compared to those ones. So I've never actually used Karma, but I think it's much more computationally intensive because it really is like tracking how these things move through the clouds and things. So it'd be really interesting to see how they compare in terms of the structures that you end up making and the kind of like amount of pressures that exist. So that'd be cool.
cool. There's a question.
Yeah, Santiago, you want to go ahead?
Hey, can you hear me? Yes. Oh, well, thanks so much. Yeah, I'm Santiago. I realize I'm in building 33, that is Earth Sciences. So, but I'm really interested in exploring these ways of looking at aerosol models beyond meat theory. I guess I just have two questions that I just thinking of what would be the next step. And in terms of, have you looked at these simulations in a situation where you have oriented particles? And like, thinking in electrical field, it could be dust in interstellar dust. And second, have you looked into, you showed only intensity plots. I wonder if you looked into polarization.
Yeah, okay, it's a really good question. So we haven't looked at maybe magnetic field aligned particles or something, but it's certainly something that people have kind of hinted at, and so it would be a really interesting study to do. So I'd be really keen to actually. Yeah, especially with the long particles, the orientation really does change the optical properties. So if there's any alignment that's preferential, even if it's not like perfectly lined up like like a magnet, even just like a preferential orientation will make a big difference to the optical properties we get from the spectrum. So
incidentally, I looked into this in the Earth atmosphere setting. There are a few measurements. People are going out there and trying to see if there is orientation with dust. And now the measurements are so much more sophisticated. They're actually doing all those measurements right now. And so anyway, so the point is that there are similar efforts here on Earth atmosphere on that regards. That regarding orientation, but can you comment on the polarization part too?
Yeah, so it was measured, but not commented on in the theory. So the way that we calculated theoretical curves was by measuring the two perpendicular polarization states of the light from the detector. But actually the rest of the theory was dedicated. I actually have another slide to show this. It was basically looking at different shapes of particles. So although one mechanism forms cubic ones, you have some shapes with different formation mechanisms that are not perfectly cubic. They're not even perfectly cuboid. So we looked at modeling, which you've seen in a little bit, different amounts of irregularity in cuboids. But actually we have the data to do a polarization study. So it'd be an interesting thing to do actually. It's all there, recorded in the lab. So yeah, that'd be a really cool thing to do. Thanks for the idea. I didn't think of doing that. So
by the way, I'm off campus today, but you're at Goddard right now, or you're visiting?
Just visiting this week, so I'm around tomorrow as well.
Okay, yeah, I'm going there this afternoon, and I plan to be there tomorrow too. So okay, I'll reach out.
Let's hang out. That'd be great. I'm over in the office with Sarah at the end.
Okay.
Or ping her an email or Slack or something, and we'll find each other.
Cool. Thank you.
Thank you.
Yeah, Santiago, feel free to get in touch. I know you have my email, so feel free to get in touch with me, and I can put you in touch with everyone.
Great, thank you. Yeah, actually, I'm going to the office right now, and I plan to have lunch there. So, okay.
Sounds good.
Great.
All right.
Thank you.
Okay.
No, go ahead.
Oh, I can't see this.
I'm so fascinated by the diversity of all of these aerosol particles, and I'm wondering if there is a typical shape or a typical, what did you call it, degree of fraction?
Fractal dimension.
Fractal dimension, because I'm wondering if we could treat it like how we treat the average weight for atoms based on the different isotopes. So what is the average fractionation? I'm sorry, I forgot already.
Yeah.
But is there like an average value that if somebody wanted to just do something incredibly quickly, they could say like, well, I know the average is gonna be, I don't know, 2.1 and plug those numbers in and see what happens.
I think it's really material dependent, and at the moment, I think it's actually, what we're doing is we're saying that for each of these fractal dimensions, we're just going to assume that the same shape particle exists in each of our different study, no matter where it is, what size it is, but which pressure layer it's in. We're going to say that shape is just our distribution is defined by that single shape. Whereas in reality, I think one of the next kind of logical thing to test is how does the spectra change when the fractal dimension changes as a function of height? Because it's a formation mechanism thing, and because lots of stuff is happening and collisions are happening and at different temperatures, and it's Brownian motion that basically puts it together. But because they're colliding and actually they are developing microphysically, one thing that Kazamasa found is that they are all different shapes. You end up with, even if you start with the same monomer sizes, collisional growth happens and they change shape as they move through the cloud and that through the pressure layers.
So
So
just a stochastic process.
yeah, you can use things like temperature and stuff to get a handle on exactly how it's changing. So his paper was showing that it kind of changed in one direction, for example, so they grew in his paper as they went up. That was the kind of conclusion that you could have. And the growth rate would change depending on different assumptions that you made about their initial kind of starting size and also what they grew into. But it's really complicated. I don't know if maybe the version of what you suggested will be the impact on the spectrum, because you have this big complicated cloud model where you have all these different shapes and then eventually passing light through it, and it's this, light's going through this atmosphere of lots of them. Maybe if we find the impact on the spectra, let's say it always moves in one direction, that's the thing you could parameterize at the end and say this is the average that we want to use. But simplifying it in the middle step would be really hard, I think. We'll see how it goes. It'll be nice to know what I really need from this actually is just a diagnostic. It'd be really cool to be able to look at the spectra and work backwards and figure out what the particle shapes were, so we can really tell. So
That's what I was gonna ask, can it be a fitting parameter that you retrieve? Trouble is, looking at the spectra, obviously for exoplanet, it's
yeah,
very minimal information.
Yeah.
That you can get. Is there other physical environment scenarios that you expect to get more, either solar system or from planet
I
spectrum?
don't know how much I can say. I'm optimistic that with the changes we've made, there might be something,
Okay.
which would be cool.
Yeah, I mean, that was sort of the original idea is. In a perfect world, you just run karma or whatever for every case, but that's computationally intractable, whereas with this sort of method. You could start to put this to a retrieval, get out the parameter, like, okay, it's a fractal dimension of this with monomers like this, and then for that single case.
Yeah.
Can you run karma and get a realistic answer?
Yeah.
Just 'cause it's a
Yeah, just
philosophical
constrain it,
approach,
makes
yeah.
sense. Because you're still just a multiplier in a sense, so you're
Mhm.
still kind of limited. You have this degeneracy, right?
Right.
And abundance and fractal size or something like that.
Yes, yeah.
So.
That's definitely especially the case with the peaks. Like, it is exactly like you say, it's just degenerate. You could either have, but yeah, something exciting's happening, maybe.
We think
Something
maybe.
you wanna tell us.
Go, just you can, I'm not.
I'm just.
Go ahead.
So the short wavelengths have been a big question for a while. People have had lots of questions about them because they don't behave in the way that theory says they should. There seems like there's a big enhancement in
Right,
what you
of
expect from
course.
theory, and
Yeah.
I don't know.
Really, it's enhanced really, they call it.
Mhm.
It's early days, but this might have something to do with it.
Cool.
And so particularly for materials that have measurable infrared features, like with JWST, if you get both the short wavelength and those features, we think that they should be, like, it should break the degeneracy,
Yeah, that
maybe.
makes sense compared to the plot you showed of the differences in long versus short.
Yeah, we think maybe that, but it'll be like material dependent for sure.
Yeah, yeah. Cool.
Vincent, you want to?
Yeah, so when you're simulating these lab data, I was curious because you have like it was like a 200 nanometer grain cube thing.
Oh, yeah.
Is that, and I'm looking at this picture now, you approximate that with a whole bunch of dipoles essentially. But do you assume that I guess you assume that these crystals are perfect and there's no essentially no like defects in it or something?
For the cubic ones, yes, these ones we
Right.
made irregular.
Right, so but even if you have like a perfectly formed crystal, it's still very likely that there's some pollution in there or some grain boundary problems where you can deform the entire matrix by having like a heteroatom or something, and that could have a really strong effect on scattering, right?
Well, so actually what this one showed is that it didn't have a huge effect. So when we did do the irregularity study, I think when people have used all of these scattering codes in any context that is not space, they get really upset if it's got an error of more than 1%.
Yeah.
Because you're doing it in a lab, and so they're like, oh, and that's the kind of thing that they'll say,
Yeah.
no, this is terrible, this theory doesn't work, it'll throw it out. Whereas for us, it's like we have to make our graph bigger to fit the error bar one. Like, like it's, but in this case, this was basically the curve that you got in theory for all these, and you can see how different these are.
Yeah,
The extremely one to the regular one. But actually, in
I
reality,
mean, it's all
yeah, there was only a difference here, really.
But what I'm wondering, for instance, if you take the second one, like the regular cuboid, right? And instead of having all perfectly aligned dipoles, instead of like having one like a potassium chloride, you add sodium chloride or something.
Yeah,
That would
yeah.
probably like distort the matrix, move your dipoles around. You might have a different dipole pointing a different direction. Would that, like, how does that affect the?
Really, really good question. Initially, I thought that was, if I didn't get distracted by the Mantra stuff, that's exactly where I was going to go. The reason we chose DDA is because it's just a really flexible theory to be able to do that with, because you
You
literally,
could just stick in a different dipole and have it point.
yeah,
wherever.
in that matrix array, like you just basically each of the 3x3 tensors is for a material type. So you basically just do, okay, it's that dipole there. Let's replace that 3x3 tensor with the different chemical, and you just basically do exactly the same math. It takes the same length of time. So it's a really easy one to do that with, but just never go around.
No, of course. I mean,
I
there's
don't know the answer, but I'd love to know.
infinite possibilities, but it's really great.
Even like a basic study of like, okay, let's just slowly increase the concentration of a impurity,
Right.
and then see when it starts changing, like diverging. Like that'd be really useful to do.
Yeah.
I need to do it really, because
Um,
I'd love to do heterogeneous materials.
You're in your fourth year, you gotta finish up and,
I keep looking at this thing, yeah, still we're making lots of simplifications. All the particles are the same size, same material.
there's always there.
But oh yeah, really good question, and I'd love to know the answer. If I do find out, I will remember and email you.
Cool.
And
Yeah.
so, you said like the size of the particles is in the order of the micrometers, right?
Yeah, we go from like 0, at the moment I go to 0.001, right? Nanometers all the way up to maybe 100 microns. That's kind of the maximum range we ever go to.
So when you increase your match, like you include like, you add like you use more monomers, meaning then like they are smaller, right?
When we do, what, sorry, when we increase?
Yeah, when you increase your mesh and just like the number of monomers that you would like to
Oh,
represent.
I see. So typically we fix the number of monomers and then basically change the particle size as the radius. So it doesn't matter whether the particles that you're representing is very, very small or very, very big. For a particular study, you fix the number of monomers, and so the dipoles themselves are the things that grow and then bigger between the two.
Yeah, okay, so and. Is like, because like, in that case, like, if you treat each dipole, like, the size of the dipole will tell you whether or not you can use like the radial approximation on each dipole that you have on the particle that you're trying to simulate.
Right.
So why not applying like your mantra to each single dipole, since like based on the shape of the matrix that you showed us, each dipole is not interacting with the next dipole.
I'm really sure of that though. I think they do interact.
I mean, based on the matrix that you showed, they only interact with the electric field that is going there, right?
No, there's definitely interaction between the dipoles. Like
Themselves?
yeah.
Okay.
Yeah.
Okay, so
In most cases, like
Okay.
if you, there are some cases where it's not true, but most of the time it is.
and which term is the one that takes into account this interaction in the matrix?
Do you want me to go back to?
Yeah, thanks.
That's all right. Actually, it's fact. Sorry, it's gonna make your eyes go big. Sorry, which,
So for example, A21XX.
Yeah.
What's the,
so this has basically got your angular wave number in there and the different positions of all the dipoles. So this is their relative positions.
Mhm.
So what it's basically doing is kind of calculating like the phase difference between the light that would scatter from this one to the other ones.
So I had a quick question about just, and this is maybe to Sarah instead, is in the lab, how well can we actually start to resolve any of the structure or the fraction, fractal nature, can we truly, without, I mean, do we look at everything in the same detail that you looked at the few particles from Mexico? Yeah, we can, that's easy to,
I mean, it's not easy, but it's very possible because they're all like nanometer to micron size. You can do that with SEM, you can do that with AFM, and we can resolve the shape and structure.
okay. Interesting. And then like in terms of of course you have to replicate the physical conditions of say a hot Jupiter in that sense. And I know you've been working on that for a while, but there's many, right, altitudes, drifting rates and all these other things.
So that's the part that like in the lab is. We basically simulate one temperature pressure cell, you could think about it in the atmosphere, and so that makes particles. And what we think we're doing there basically is getting the nucleation size, but then how they grow. We immediately go there to a microphysical model or something.
So you kind of feed in the.
Mhm.
We could always do more lab stuff though, like seriously, it's so useful to have any sort of
Yeah.
those things, like the haze analogs that we have, like that kind of data. I mean, it goes to that same idea of can you summarize it? Like in reality, if you want to make an actual proper haze, then all these particles are going to have to be different sizes, like every single one's going to have to be a different shape. And so modeling that would take a long time and it might still give you the wrong result. Whereas like if you can get someone nice to do it in a lab, then lab people are useful.
Awesome. Well, I think we need to call it there, but I think Matt's around this afternoon, and
Yeah.
maybe a little bit longer. So get in touch with Sarah or I, and we can put you in touch if you want to chat some more. But let's thank Matt again for the awesome talk.
Everybody.
Thanks everyone for coming online. I'm going to end the meeting now.